Okay, let's continue talking about the critical mass energy density of the universe. And so just as a review, I've written it up here that the critical mass energy density is the density that is going to be necessary in order to stop the expansion of space and time. So when we talked about the birth of the universe, we said that the universe was teeny tiny, and then it started to expand into the present universe. So in order to describe teeny tiny objects, we had to use quantum mechanics. Now, in order to describe the universe as it exists today, we have to use concepts of the general theory of relativity as proposed by Einstein. So quantum mechanics will explain teeny tiny objects, and then large objects have to be explained by using the general theory of relativity. And so this is one of his representative formulas. So it turns out that there's actually 10 of these equations that have to be solved at the same time, and they have to be written in terms of calculus and then also in terms of tensors. So they're very, very difficult to solve. And this is a typical one. And then when Albert Einstein originally came up with this formula, this term right here was not there. So I'm going to erase it. So this term was not part of his original theory of general relativity. Now, if we look at this term here, you notice it's got a big G in it, and then that big G is the gravitational constant that comes from the force of gravity. And so this term right here is going to cause the universe to collapse. Okay? Now, when Albert Einstein came up with this theory, the astronomers of his day said that the universe was collapsing. Now, Albert Einstein did not like that. Albert Einstein thought that the universe ought to be static. The universe should not expand and the universe should not contract. And so if the universe is collapsing, I need to do something about it. And so what he did was he inserted an additional term into his formula. And so he inserted this one, where this is a fundamental constant that he just invented. He had no proof that it existed, but he just went ahead and threw it in there anyway. So this would be a fundamental constant of nature, and then this term here is another tensor, which makes the whole equation work. Now, you don't need to know about any of the names of these various pieces of the formula, with the exception of this one right here. That one is very, very important. So Albert Einstein just goes ahead and throws that in there, and then he said later that it was the greatest blunder of my life because I never should have just arbitrarily stuck a variable into my equation just because I did not like what the universe was doing. Well, even when Albert Einstein was making a mistake, he was doing the right thing, because it turns out that this thing here is going to be related to dark energy. So mass causes the universe to collapse because of gravity, and that's this term right over here because it's got the big G thing in it. Well, this term is going to be something that opposes the collapse of the universe and is causing the expansion of the universe. And so this one here is going to be called the cosmological constant, and it is basically dark energy. So the more dark energy there is in the universe, the greater this constant is going to be. So even when Albert Einstein was making a mistake, he knew what he was doing. And then if you were to take into account the amount of mass that is causing the universe to collapse, and then you combine it with the amount of dark energy, which is causing the universe to expand, that then is going to be the energy density of the universe. So the question is, which of these two terms is winning? So if this term is winning, the universe is going to collapse. If this term is winning, the universe is going to expand. Now, if these two terms were equal to each other, then the density of the universe would be the critical density. So that critical density is the amount necessary to stop the expansion of the universe. And so that would only happen if these two terms were equal to each other. So before I go on, I did want to show you this. How does relativistic mechanics compare to classical mechanics? So classical mechanics is what Sir Isaac Newton would say. And if you recall, Sir Isaac Newton had his second law of motion, which said that a force causes a mass to accelerate. So notice that this F is what's doing the pushing or the pulling. And then the A over here is what's happening. So because of the force, masses accelerate. And then we found in our lesson on fundamental particles that the force of gravity could take the place of this F. Okay, so that the force of gravity was minus big G m1 m2 and then divided by r squared. So that would be the force then, and then on this side over here, instead of m, we could say that it's m1 and then a, and then we could calculate what would be the force of gravity acting on a mass m. And what we found was that it would cause a planet to go into an orbit. But then we found that in order to account for dark energy, what we could do was we could modify the formula. And so instead of it being this, we could add on an extra term. And we said that it was a term that was positive to counteract the negative, and it was some force that depended on R. And then put the equal sign in there. So we need to add one additional term, and then the effect of this term would be to expand the universe. This would be anti-gravity, and then this would be regular gravity. Well, look here, this thing over here has a plus term, and this thing over here has a minus term. So that this is the thing that's causing the gravity, that's causing the shrinkage of the universe. This is the thing that's expanding, and then this would be the classical way of explaining it. And then this term over here on this side is what is this doing? What this thing is doing is it's curving space and time on this side. So are you ecstatic at this point? You know, you should be jumping out of your seat. This is so cool that we can show how general relativity is similar to classical mechanics. You're not excited at all. All right, okay, I can go with that. All right, let's take a break. When we come back, we're going to talk about the different curvatures of space and time.